start then. So yeah, before going into the subject, can you guys tell me like anyone can unmute and tell. So what are the things you are observing in this particular picture?
Sir, an aeroplane flying in the air,
Okay.
covered, is covered in fog,
Hmm.
surrounded by some fields and clouds.
Okay. That is anyone like who is not having any aerospace background or aeronautic background can tell. So as a aeronautical student or aerospace student, what are the things you can observe?
Sir, an aircraft flying with
It's
two
it's a
turbo
low-wing
fan
aircraft
engine.
having
Okay, yeah.
yes.
So one guy came up with one answer, low-wing aircraft, and then
It's a passenger aircraft with two turbo fan engine.
nice. Then
It is a low-wing aircraft.
okay, yeah. So that is established. So any other difference you can make, or any other things you can say? So you see here. So it is first of all, it is not a conventional aircraft what you see as a transport aircraft, right? Usually what you see in conventional aircraft, what happens? Like it will be either mid wing or little high wing, and your engines will be attached to the wings, right?
Yes, yes.
Yes, sir, yes.
Yeah. So that is the major thing. And other thing is like you should have observed the tail. Where is the tail?
It's
Is
the
it,
T-tail
yeah. So that is a
configuration.
high tail, right? High tail configuration or T tail configuration. It's a very unconventional design of an aircraft. Like so you will be studying this aspect like the where if you place your wings or tails or this engines in different parts of the fuselage. So what is the stability characteristics, and you will be studying later. But the moment when you see like this is what I'm saying. As a student who is preparing for a gate kind of an examination, whenever you see a question, you should be able to identify the difference or the important things within the question, which will actually define that particular question correctly. So you should be able to take out important things out of the given question. So that is why I kept this image, because anybody can say this is an aircraft which is flying, right? So that is not what you are actually looking at. So if you are given some particular question in a gate, so like this is coming from some particular concept or some particular topic, whatever you studied, but you should be able to dissect like what is the given information and what are all the given information which are important for you to solve the particular question, like that. So you should be able to think in a different way. That is how the gate works from the perspective of your engineering exams to gate exam. This is how it makes a difference. If you know your concepts really well, you should be able to pick that important things out of the given question. Okay, then solution is not a big deal. The main problem relies on to understand the given problem correctly. Okay, so now we will go on to the topic. Okay, so first what I'm going to do is like I will just define this total or stagnation properties, which is basically we will be using extensively across the our subject. So we will be basically using like P naught, P naught, like are the ratio of P naught 2 by P naught 1 in compressor, or P naught 3 by P naught 4 in the turbine, like that. Like we will be using this total properties a lot. Basically, whatever we do in propulsion, we will be analyzing engine characteristics or thrust equation or any efficiencies. Whenever we define, we will be using this total or stagnation properties as a reference. So like we will be using this a lot. So now I am asking you a question. You guys are already been aware of what is total or stagnation properties. Can anyone define what is a total temperature? You can just unmute and say. Whatever you know, you can define, no problem. Right? Anybody has any definition? At least what you learned. Okay. Okay. If I am right, you guys must have studied a total definition, total properties in this way. When a flow is brought to rest adiabatically, the corresponding temperature, you will be calling it as a total temperature, right? Right? So if guys remember, you write like T0 is equal to static temperature plus dynamic temperature, C square by 2 Cp or kind of right? So this is how you must have studied the definition of total temperature. Similarly, for total pressure, you might have defined it as when flow is brought to rest isentropically, right? So the thing is that is actually a half-cooked definition. That's the point there. Like it is not just when a flow is brought to rest adiabatically, you cannot just define a total temperature like that. So the one more important aspect we will be missing while we read a textbook, right? So because this is how the textbooks usually defines when you bring a quantity to zero velocity in a certain process. So you will define a quantity, but that is the definition in a half cooked way. So we will basically see what we are actually missing. Okay, so we will assume whatever it is required, like first is a frictionless and adiabatic flow, sorry, or no body force and adiabatic flow, not necessarily a frictionless. So we are just using the energy equation. I am not going into the detail. In actual classes we will be dealing with how we are coming up with this particular form of energy equation. I'm just taking the energy equation for no body force, F refers body force, F is equal to 0, and no heat transfer. Okay, so for this particular condition, my energy equation can be written in terms of d by dt of E plus V square by 2, where E is internal energy, right? So, and V is velocity and P is pressure, that is a scalar, where velocity V is the whatever it is in bold, that is a vector. This is as a magnitude, so it is written as a scalar because it's a magnitude. Okay, so now this is my energy equation. So this part, again, I am not going into the detail over here, but still this is a vector relation. It is just a divergence applied to a scalar times a vector, right? So it is we have to understand, we cannot just take this quantity out from the equation, because though it is a scalar, still it is a function, right? What is divergence? You guys have already studied in your mathematics, right? Divergence or del operator. I am not going to use it as a divergence here. Del operator. You guys have studied dou by dou x of I plus dou by dou y of j plus dou by dou z of k. So this is a special derivative operator. So when it is applied on a vector, so then you call it as like divergence of a vector, that is a dot product. That's basically you're multiplying with individual component to other one, inner product, right? So but there is one more scalar sitting over here, so which makes this one, so we have to use vector identities. So that is P times del dot V plus velocity vector times grad P. So when del operator applied on a scalar, it is a gradient because we cannot apply a dot product to a scalar, right? So that can be written like that. So again, we are not going into the details now, but I'm just saying how the process goes. Okay. So similarly, we can define a d by dt of p by rho. It is just a what you call um, anything like u by v rule, d by dx of u by v rule. That's what they are applied. So again, that's not important. The thing here is at the end when we do algebraic simplifications to this particular energy equation, so we will end up with one particular term. So that is nothing but E plus P by rho is written as H, that is a thermodynamic property. So internal energy plus flow energy is nothing but enthalpy. And we will be end up with one more term. This is very important term because this particular term we will forget while we are defining a definition of a total property. We just define when the flow is brought to rest. Like if the right hand side is 0, then when we say like flow is brought to rest, that means whatever it is there in the inside of a differential operator, so that will basically becomes h plus v square by 2 is equal to constant, right? So like if derivative of something is 0, it's like dx by dt is equal to 0, that means x should be constant, right? So that is how the derivative works. So similarly here also, if right hand side becomes 0, that means you can safely define h plus v square by 2 is equal to constant. This is nothing but our definition of total temperature. But the thing is what happens? This is just a fruit for thought for you guys. What happens considering all other assumptions what we started with are valid if the flow is unsteady? So can anybody say? What happens if the flow is unsteady? The right hand side cannot be 0, right? It's a function of time now. So then the definition the very definition what you started off with is not valid if the flow is unsteady. So this particular part we will be missing in that particular definition when we define the flow is brought to rest adiabatically or something. So the important assumption we have to make here is the flow has to be steady, or the process has to be steady, so that the quantities will not change with respect to time. So we have to take time out of our equation, then only we can actually define these particular quantities, right? So then it's straightforward. Like if the right hand side becomes 0 when we assume it is to be steady, so then we can write it as it is equal to constant, and we define that constant to be a stagnation enthalpy. Or if it is perfectly like calorically perfect gas, again we can go on and define this particular quantity to be h naught is equal to constant throughout the flow. Only when every streamline whatever you are dealing with is originating from the same source and it's a uniform, right? So and calorically perfect gas, you can always write h is equal to cpt. That we will see how we are these quantities are actually defined in a broader picture when we come to normal classes. So for the sake of demo, I am just giving you the overview. But so you can say T naught is equal to constant. The important aspect I wanted to stress out over here is the way how you define the quantities is not always exactly to the point. So what you understand and what you have read and what you understand about the physical quantities, there will be a missing link, because textbooks they don't go into the details of all the aspects. Their assumption is like you are already aware of some of the prerequisites, but the part is sometimes you often misinterpret what is actually given in the textbook definitions. So that's the point. Like gate is all about understanding your particular concepts to the point. So then only some of the questions whatever given in the paper you can actually understand in a proper way what it like what the questionnaire like he or she when they set that particular question they will be tricking you over these particular concepts only because they know where you can make a mistake. So that is how they will prepare a question. So if you are aware of your concepts to the point, then there is no chance that you will be making mistake. So that's the point I wanted to convey over it. So like this is how basically in my classes, like every particular quantities we will be defining in a more precise way, so that you are at least you are able to appreciate what they actually mean, and you are also able to look the same concepts or whatever you studied so far in a different viewpoint, which is a more useful for you to understand the further topics. So that is how we will basically deal in our class. Okay, so I know so like what we can do. So now this is just for a demonstration. I didn't go into the details of every aspect like how we derive those equations and all, so that we will be dealing in our actual classes. But the idea here is basically in my classes I will be dealing more of a uh, theoretical way how to understand the particular topic or the quantities whatever we study, whatever we use, or whatever formulas you actually use, what they actually mean and where they actually valid and where they are not actually valid. Those are also a very important point. Like it's just not remembering formula to solve such particular questions. It is also important where that formula is not useful, so to solve certain set of problems. So they are all like you can make those distinction only when you are able to understand the topic to the point. So like so if you are able to understand the point topic completely, then you can able to make that minor distinction where it actually needs, like so that we will study over the period of time, like when we go with our actual classes. Okay, so now similarly, like this is why I define that particular quantity is like we will be using this quantity extensively, because like when you want to write a work done, you will be using again Cp T02 minus T01. When you want to define a heat transfer in a combustion, so again you will be using T02 and T01. Like these are all like very basic things what we use when it comes to a propulsion. Basically propulsion is kind of a marriage between fluid mechanics and thermodynamics. Like you will be combining always these two part together. So that's the funda between like fundamental prerequisite, so I can say, like to study the propulsion as a subject. So that is why like these quantities are important when you are defining, even when you define your uh, what you call efficiencies and all. Like you will be constantly replacing this term, like whenever you have T naught by T, you will be replacing it with like pressure ratio across compressor is given to you, or overall pressure ratio of a compressor is given to you. You will be just using this particular definition. The thing you have to remember is like the background of that particular definitions too. That is why I am just giving an example where we use these particular quantities. That's it. Okay, so now the second part, so I was talking, so like yeah, so I'll momentarily stop here. So are you guys able to see like what we discussed so far? So like are you able to make any sense out of that, whatever I actually discussed about total properties,
Yes.
right? So because yeah, that's important. Yeah, I know, like I didn't go into the details of every aspects there, but the rough idea I was just given. Okay, so now The second part is a thrust equation. I am not going into the thrust equation here again because it's again involves a derivation part of thing. As per the demo is concerned, I am not going into the details of thrusting. Okay, but when it comes to a jet propulsion, we know like this entire system can be treated as yes. Anybody has question?
Yes, actually, my question is that is there any book particular book which you followed, which followed by our institute? Like, is there any book, particular book are we follow? Hello.
Basically, like I usually follow this Cohen and Rogers for propulsion. Okay, and the other than that, like I will always suggest you guys to go through other books, thermodynamics, the thermodynamics by Moran and Sheffer, and other one book I can suggest is aerodynamics by Anderson to understand these concepts in a very neat way. Okay, so yeah, these are the books I'll be following, and of course for numericals you guys can refer veganation, and be careful, there are certain notations which will always be confusing. As long as you are clear with your concepts, you don't have to worry for whatever mis print was there in the particular notation in that book, so you will be able to recognize that. So yeah, for numericals you guys can refer veganation because there are plenty of numericals you guys can solve. And yeah, so these are the
Okay.
books I will be following.
Can you please provide us at the end of this session, sir, all the books which we need to follow, like this books we can like.
Okay, yeah, the thing is like you guys have access to our IGC materials, right?
Yes,
Sir.
sir. Yes, sir.
Yeah, so if you go through that propulsion material, so there I mentioned what are the books you guys can refer.
Sure,
So
sir.
yeah, you guys can always refer that one. There I mentioned the references, so you guys can always refer that. Okay. Okay, so we will come back to our discussion. Okay, so again, the thrust equation we are not going to derive today's class. The thing here is like, so whenever you see a engine, the analysis of an engine is like a different way. Like you can treat entire engine as a black box when you want to deal with the thrust equation, where you are interested in what is coming in and what is going out. You're not interested what is going to happen inside. That is none of your business when you are dealing alone with the thrust equation. That is why you see whenever you see a thrust equation, you see with like mass flow rate of the air which is coming in, and what is the velocity at which the jet is exhausting, and what is the velocity at which air is entering the engine, and what is the pressure difference at the exit of an engine, and what is the ambient pressure. That's it you are basically concerned about, right? So that is called in a fluid mechanics, that is called a control volume approach. You guys will be studying these things in your fluid mechanics. So the control volume approach, it basically tries to relate your Newtonian mechanics. So Newtonian mechanics is like essential to deal with like most of the mechanical related problems, right? So when you apply a Newtonian mechanics to a fluid which is basically moving around, which is not a fixed in space or something, how you want to apply how you are going to apply the Newtonian mechanics. Newtonian mechanics is applied for a rigid bodies, right? Like that is how you study in your at least from your high school levels, right? So basically, like car moving or some ball is moving and hitting to some object, like they are all rigid bodies. Like you will be considering there, where entire mass within that particular body is always fixed, right? Right? Are you guys able to recall these things? How you guys applied Newtonian mechanics,
Yes, sir.
right? But when it comes to a fluid, it's like how you are going to apply, because some fluid is coming here and fluid is going there. Like it is not a rigid, like it's always varying, right?
Yes.
that is where you have to appreciate the idea of this control volume methodologies. Like it is basically coming from your Reynolds transport theorem. Those things you will be studying in your fluid mechanics. At least I can say, like, you must have studied in your BTech courses, right? This Reynolds transport theorem or control volumes and those kind of ideas.
Yes.
Yeah. So here we will be giving some more idea of that one. But the important thing we have to understand here is, like, for any given fluid mechanics problem, we can approach the same problem in three different ways. One is integral, one is a differential approach, another one is a molecular approach. Molecular approach, of course, we are not dealing with, because as an engineer we are not basically looking these aspects from a molecular point of view. So but we will be using two different ideas to solve. Like one is integral approach, other is a differential approach. So the integral approach is nothing but this control volume kind of analysis, and a differential approach is what we will be using to understand some of the theoretical concepts. Also, when you want to set up this particular problems in a simulated environment like CFD or those kind of thing, where you basically have to solve set of differential equations to attack that particular problem. That is one more way to look at the problem. And one more important idea is there, that is the dimensional analysis, that we are not dealing here. We will be I will give that particular dimensional analysis analogy when I deal with the fundamentals of propulsion, where I bring that concept into light, because we will be using some of non-dimensional numbers. When we, like, you might have aware of Reynolds number, Mach number, they are all non-dimensional numbers. So the making non-dimensional quantities from given physical variables, that you guys also must have studied in part of your courses, like Buckingham pi theorem and all, you must have remember. Or even if you don't remember, it is fine, like we will be dealing in our class. So the thing here is, like, we have to understand as well as able to appreciate the different approaches, why we need so many approaches, because, like, every problem can be attacked in single way, but still we use a different approaches in different part of the topics. Why we are actually, because to understand the physics, that's what important to us, right? Whichever leads to that particular physics, or explains that particular physics well at that particular scenario. So that is a better way to approach with. Like when I start with the thrust equation, the control volume seems easy. Like if I go through the same control so thrust equation derivation from the perspective of differential equations, it might take a longer time to arrive at the same conclusion. As part of the classroom studies, we don't want to spend a lot of time to understand the same subject, right? So we can approach in a different way, and still we can able to understand the underlying physics there. So that is one more thing, because we will be using this control volume analysis a lot. Like whenever we, even with when we deal with just a combustion chamber, or just a compressor, or just turbine, or just the nozzle, we'll be using this control volume approach alone. So that is easier for us. Okay. So in that sense, so this particular equation is derived from that approach, so that we will be dealing in our actual classes. So now what I am going to do is, the concept, the small derivation, whatever we are going to deal in this today's demo class, is restricted to this particular element called a combustion chamber. So now the question is, so can you guys tell me what is the role of a combustion chamber in gas turbine engines?
To ignite the fuel mixture in air.
Okay, then so let me just ask you in a different way. What is the physical need, or the demand which in a cycle, if you take it as a cycle, right, like you will be having a compressor, you will be having a combustion, and you will be having the expansion, and it will be exhausted, right? So in a cycle, what is the need of combustion chamber? Like, what is the need of combustion? What you do basically when you consider it as a cycle?
It will increase the mass flow rate.
Mass flow rate increase is not much, right? Like when you compare to your actual mass flow rate, the mass flow rate of fuel is nothing else. Like it's a very fraction of total mass flow rate of air. Like it will be less than one. It's very less than one. The basically what you do, you will be adding energy, right?
Yes, sir.
So in the form of fuel, when you are burning the fuel, what you are expecting out of that? It's just take an example of your own bike or car, whatever you are driving. Why you need petrol? That basically drives, right, your vehicle. How it drives? The driving mechanism, whatever it is connected to your physics. But you need certain amount of energy which has to be burned to move forward your vehicle, right? So that energy basically where it is coming from? It's coming from your fuel, right? The fuel will be containing some kind of um, energy, so that will be converted into a useful form using a process called combustion, right, where you will be increasing the cycle temperature to certain level so that you can again drop the temperature. So in the expansion process, that energy will be converted into whatever the thermal energy you had, that will be converted to a kinetic energy in terms of when it comes to a jet or this kind of thing, right? So basically combustion chamber is the important part. Important role of a combustion chamber is to give that particular energy which is required to sustain that particular cycle, right?
Yes, sir.
Yeah, so I will be just going with that particular combustion chamber, or how that energy is actually related. That one we will be seeing now. You see here, basically what is how the combustion process happens in our gas turbine cycles. Can anybody tell, like, what is the kind of process, the thermodynamic process it involves there? You guys have studied, right? Like isochoric, isothermal, isentropic kind of processes. What kind of process happens in combustion chamber?
It's isobaric.
Isobaric. What do you mean isobaric? Like the pressure has to remain constant, right?
Yes, sir.
Which pressure are we talking about here? Is it a static pressure or the total pressure?
It's a static pressure.
No. It has to be total pressure, right?
Yes. Sorry.
Yeah. It has to be total pressure. So the total pressure is what you tells you more about your energy content in the flow. So because whenever you say like the total pressure loss, to overcome the total pressure loss only you are doing so many exercises. Why you have to do that exercises? Because the total pressure is the direct measure of energy content of the flow. If you are losing the total pressure, that means you are losing the part of energy in a non-useful way, right? So that is why very important aspects. We will be dealing with total pressures. Okay, so that means the combustion ideally has to work with maintaining the total pressure. Like if P02 is what, like if I have a combustion chamber in a control volume ideas, so something is entering over, something is going here, so you will be supplying some Q in, that is a heat. Okay, so now here you have some values P02, P02. Similarly, here you will be having P03, P03, right? So in ideal scenarios, P03 should be equal to P02. That is how the process has to work. But in a realistic way, what happens? You cannot maintain the total pressure constant, so that you will experience some kind of pressure loss. So this PL, whatever we are seeing here, that is basically a pressure loss. That is nothing but the difference between the total pressures in the beginning and at the end. That is nothing but my pressure loss. This is an actual problem. Ideal way they are equal, but in actual cases you will feel some pressure loss. So that is one of the important aspect when you deal with the combustion process. But now the thing is, I told like I will be going to derive one small equation that basically connects our combustion chamber mechanism. So I will be starting with my energy equation. What I am going to derive here is what is the fuel you have to add to increase a temperature at T02 to T03 in a combustion process. That's basically what like as an engineer you should be very aware of. Like you should be aware of how much fuel you have to consume, right? So for that one, that particular part we will be dealing, and so we will be dealing from our fundamental understanding how the energy equation work. Basically, we will call it as SFEE. What is SFEE? Steady flow energy equation, or the first law applied to a flow process, right? You have studied this thing in your basic BTech courses or even in thermodynamics classes. Steady flow energy equation. What does the steady flow energy equation basically says? So considering all other process, nothing like which is not contributing to your flow, only the contributions are from the energy level at the entry station 1 and what is the energy level at the station 2, and whatever in between you are adding as an energy, nothing else. Like what happens to change that energy you are not interested in, you are just interested in what is there at the entry and what is there at the exit and what you are adding into the system. That's it. It is basically deals with system boundaries,
Okay. Sir,
right?
I have a doubt.
Yeah,
Sorry to interrupt.
no problem. Yeah.
Sir, okay. So within this, there you have shown me a control volume approach where energy is added.
Hmm.
So we need to consider here is a total temperature, that is a stagnation temperature.
Hmm.
So, but my question is, uh, where we actually consider the static temperature, is it certain point inside a control volume or what? So where
No,
actually the static
the thing
temperature
is,
concept comes?
you have to remember the part here. Okay. So this stagnation temperature, whatever we are talking about, they are not the actual quantities. They are all the defined quantities. You see, they are all the defined quantities. The actual quantities are your static quantities. Static pressure, static temperature, those are the actual pressure and temperature at that particular point. But
Okay.
at the same point, we can define these quantities. So like if I define basically like I am bringing at that particular point, say like I have one streamline over
Yeah.
here at some point, so point 1, I have a pressure P, temperature T, density rho, and those basically sets my thermodynamic properties of the state, right?
Yes.
If I have a Cartesian coordinate like that, P rho and T, so some point based on what is values of P rho and T that sets the state, right, of that particular particle at that particular point,
Okay.
right?
Yes.
Similarly, in a fluid mechanics point of view, the velocity vector, whatever you have,
Yeah.
that particularly says what is the magnitude and at what velocity the fluid is moving at that particular point, right?
Yes.
Yeah, when I want to relate these two things, basically what happens, these quantities can change because it's a moving system.
Yes.
So the thing what we can say is like at this particular point, if somehow I forget about what is there downstream of this one, I forget about what was there upstream of this one, I'm just focusing on this particular point. If this particular point is brought to rest, like V is equal to 0, in such particular way that the process is steady
Stagnation.
and isentropic, or I will call adiabatic, and no frictional losses, or I can say reversible, right? If I bring this particular point, imagination, it is not actually how you are doing. In an imagination way, if I bring this particular point to 0, then what, like, because now what happens if you are bringing V to 0, that means something has to change over here to balance, right? Like that is the state. You don't want to mess up with the state of the system, right? Thermodynamically, they are at some state, right?
Yes. Yes,
So
sir.
now what you are going to do, your P, T and rho will adjust accordingly, so that when it comes to rest, you will get a new state called P naught, T naught, rho naught kind of thing.
Stagnation properties. Yeah.
Correct. So that is a defined quantities. It is not actual quantities. You
Yes.
see?
Okay.
Yeah. So similarly, like you might have studied, like when you want to measure a velocity, you will use a pitot static tube kind of thing, right?
Yes, sir. Yeah.
So you will use like this, and what happens at this point, you will call the whatever it measure is a P naught, and if you measure in a normal direction to the flow, then you call it as a static properties P. Why you are calling it as a P naught? Because locally you are bringing the flow to rest, right?
Yes.
So some quantity was here that is coming to rest at this point. When it comes to rest, this particular state is
P naught.
becoming to zero velocity. In an
Yeah.
assumption, what you are making is like that is coming to rest adiabatically or isentropically. Gas is in an incompressible flow field, so definitely you can treat that one,
Yes.
right? So this is because this is what you measure actually. Now you are actually measuring, but what you are measuring, this is not true indication of the pressure of the flow, like what the flow field actually having. The static
Yeah.
pressure of the flow field is not what you are measuring here. You are measuring
Yes.
the total pressure, but the
Yeah.
static pressure is very different. This
Yes.
is actually flow is carrying,
Okay.
right? Yeah.
Yes.
So that, yeah, okay. Yeah, we were little off from the subject now. Okay. So we will come back now. That was a good question. So we will be dealing that those things in when we actually study in our classes. Okay. The
Okay, sir.
thing is,
Thank you.
yeah. So now here the energy equation is what we are looking for. So I have energy equation. What is first law of thermodynamics basically? What is the physical principle or thermodynamic principle which says first which governs the first law of thermodynamics?
It's equilibrium, I guess. It deals with equilibrium.
What equilibrium?
Uh, if uh, if two systems are equilibrium, I mean, if first and the third system is in
No,
equilibrium with each other.
You're trying to define
Zeroth.
zeroth law. No,
Yeah,
no.
yeah,
I'm
yeah,
talking
yeah.
about first law of thermodynamics. What is first law of thermodynamics?
Uh, it deals with the internal energy.
Okay, what is
Sir,
the physical principle? You say.
energy can neither be created nor destroyed.
Ah, okay. So if you want to state that in a two words, what you say? Conservation of energy, right?
Yes, sir. Law of conservation.
Right. That is nothing but your first law of thermodynamics, right?
Yes,
What does it basically teaches you? The energy can neither be created nor be destroyed. That's the statement or elaborative way to say that. But conservation of energy, right? So basically, if you have a system, so say Q is equal to, you can write U plus work, where U, if I say it is a change in energy or something, right? Or delta Q is nothing but delta U plus delta W, like that you will define, right? Right? This is how you define your first law of thermodynamics mathematical way, right? Similarly, if I have a system like this, so if I apply the first law of thermodynamics, that basically says is like my energy cannot be destroyed or created, right? It has to be conserved. So that is what we are going to do here. What we are going to do, so here the measure of energy is through enthalpy of a system. H02 over here. I have H03 over here. Why this is a measure of energy? We define H is nothing but P by rho plus E, right? Or energy plus PV. This is nothing but H. This is how we define H in thermodynamics, right? So similarly, so this is a measure of energy, like the flow work. If I just look into this particular form of energy, that is nothing but internal energy plus flow work. The delta W, whatever I'm saying, is flow work. No shaft work, just the flow work I'm talking here. Okay. So H02, H03. So that has to be same. Sorry, that has to be balanced as part of the conservation of energy. How it is going to balance? That is nothing but energy at the end of the system will be equal to energy at the beginning of the system plus whatever energy you added as a heat, right? So this has to be conserved. You cannot change that. That is the law. So that is what we are doing here. See, H0 I am defining in terms of CpT03, and also of course this is per unit mass, but here I cannot treat it as a unit mass because here I am entering with mass of air, here I am entering with mass of gas, where mass of gas is nothing but mass of air plus mass of fuel. So this is not per unit mass system. So I have to multiply my mass of gas to here, mass of air to here, similarly mass of fuel to here. So now, so these are where the small letters represents your what you call intrinsic properties and extrinsic properties, like that you defined in your thermodynamics. You guys can go back and check. So here what we are going here, mass flow rate of gas times CpT03, which is equal to mass flow rate of air, which is entering over here, times it is again Cp gas, where it is Cp air, times T02 plus mass flow rate of fuel times whatever the calorific value of the fuel which actually carries. That is basically a measure of how much energy you can get out of the given fuel, right? So now if I do the simple algebraic manipulations here, like just a simplification, I am using m dot g is equal to m dot a plus m dot f. That is, what is this one? Can anybody recall what is this particular law? It is basically coming from your fluid dynamics. What is that one? That equation? Mass flow rate of gas is equal to mass flow rate of air plus mass flow rate of fuel. It's basically continuity, right? So now, so if I just substitute mass flow rate of gas is equal to mass flow rate of air plus mass flow rate of fuel, so I can always make a variable separation. So where I am segregating all quantities which are connected with mass flow rate of air one side and which are connected with the mass flow rate of fuel one side. So what happens? I can make a right and left hand side like this, which connects only a mass flow rate of fuel and which connects only mass flow rate of air. And I am defining one more new quantity F. That is nothing but mass flow rate of fuel by mass flow rate of air. I am just taking this mass flow rate of air outside from this equation so that it becomes 1 plus F, right? So now what I am doing, I can cancel out this mass flow rate of air from both sides because I am basically segregating now. Whatever is remained, I am writing in terms of F. So this is the very important equation. Based on this, so many gate questions have been asked. Like basically it is a repetitive question in gate. Like if you see, like in every year one question will be there from this particular formula. So this is, but the idea here is like you have to understand the energy balance in the system. You don't have to remember this equation at all. You don't have to remember this equation at all. If you know your basics well, it is nothing but a steady flow energy equation applied to a combustion system. That's it. From there you can easily get, like, you can start off from balancing the energy and you can just derive and use the fluid mechanics idea, is mass flow rate is conserved, right? This equation you will get, like, so this is how, like, the derivation part is also plays an important role when you want to recall a formula. If you don't remember the formula, still you can arrive at a formula in a given environment. So like it hardly takes 1 or 2 minutes, right, to derive this formula. It is not more than that. You can still arrive at a given solution. Okay, so anybody has any question? So we can take 1 or 2 numerical based on this particular formula. But anybody has a question so far? Okay, if nobody has any question, we will go for one numerical. Okay. Okay, so this is a question, like, air at 450 Kelvin stagnation temperature and at a rate of 50 kgs per second enters the combustor of a turbofan engine and is burned with 1 kg per second of aviation kerosene, and heating value is given 44 megajoules per kg. The specific heat at a constant pressure, that is Cp, for an incoming air and the burn products, so both are given, Cp of air and Cp of G, to be 1005 and 1147 joules per kg Kelvin. Units are important. Considering 100% burner efficiency, the stagnation temperature at the exit of the combustion is equal to. So what are the things it is given in this particular question? Again, we will draw a simple control volume diagram. So air is entering with some property, air is exiting with some property, and you are adding some heat, right? So for you, the QV is given 44 megajoules per kg. Similarly, stagnation temperature at the entry is given T02, which is equal to 450 Kelvin, and mass flow rate of air is given, that is 50 kgs per second. Similarly, mass flow rate of fuel is given. At this mass flow rate, you are adding that particular kerosene, that is 1 kg per second, and Cp and Cv, of course, is given. Cp of air 1005 joules per kg Kelvin. Similarly, Cp of gas is given to be 1147 kg Kelvin. So now all you have to do is to calculate what is the temperature rise which happens, like not exactly temperature rise, and what is the temperature at the exit. T03 is equal to what? That's the question. So straightforward, right? So again, we will be dealing with the energy balance. What is energy balance? H03 should be equal to H02 plus whatever, sorry, not, I will write in capital letters, that is total. H02 plus m dot f times QCV, right? So H03 is nothing but m dot G CPG T03, which is equal to m dot A Cp of air T02 plus m dot F QCV, right? So now they are asking us to calculate T03. So now you don't have to use that particular formula. All you can use is, all other quantities are given to you. just write T03 is equal to m dot a CPA T02 plus m dot at QCB whole divided by m dot G CPG. That's it. And m dot G, of course, you have to calculate. M dot G is nothing but m dot A plus m dot F. So that is 50 plus 1, 51. So if you substitute all the values, can you guys tell me what is the answer you are getting? Anybody? Are you guys able to hear me? Okay. So anybody got the answer? I given the final form. It's a very straightforward from here, like it is. Right? If you substitute all the values given here, m dot A, T02, CPA, CPG, m dot F, everything. So, and m dot G, of course, you have to calculate from continuity. And you should be ending up with 1138.73. One decimal place they are asking. 1138.7. Right? Kelvin. And they are not asking you to round off or nothing, just one decimal. Whatever you get at the first decimal, you just keep there. Right? Similarly, this is one more question asked in 2021 gate. The airflow rate through a gas generator of a turboprop engine is 100 kg per second. The stagnation temperature at the inlet and exit of a combustor are 600 and 2200. The burner efficiency is 90%. And the heating value of a fuel is 40 megajoules per kg. The specific heats at constant pressure of air and burned gas, again given Cp of air and Cp of gas respectively. The flow rate of the fuel being used. So now they are asking mass flow rate of fuel. So again the problem is same, environment is same, only the variable you have to calculate is different now. They are given T02 to be 600. Similarly, T03 equal to 1200. Similarly, mass flow rate of air is given to be 100 kg per second. Similarly, calorific value of fuel is given to be 40 megajoules per Kelvin. Sorry, megajoules per kg. And one more thing they are given, efficiency of a burner, that is 0.9. So we will see where it comes in equation. And the other thing is Cp of air, Cp of gas is given to you. All you have to calculate is what is mass flow rate of fuel. Straightforward. Again, start with our basic conservation of energy equation. H03 should be equal to H02 plus m dot F. Now efficiency is there. Not all the fuel value, whatever your calorific value you are giving is actually converted to energy. There will be some loss. So that is accounted by efficiency of the burner times QCV. Straightforward. Now if I write it in terms of mass flow rate of gas, Cp gas, T03 should be equal to mass flow rate of air, Cp air, T02 plus mass flow rate of fuel, burner efficiency times QCV. So now if I use m dot of G from my continuity, that is nothing but whatever mass is entering should be equal to whatever mass is exiting. So two masses are entering, so air and fuel. So gas is exiting. So that is conservation of mass. So now, so if I write m dot G in terms of that one, so I can take m dot air outside, that becomes 1 plus F times CPG times T03, which is equal to again m dot A CPA T02. If I take outside m dot A, that becomes F eta B QCV. So I can write m dot cancels. I can write in terms of F, that is nothing but I will get like CPG T03 minus CPA T02 whole divided by eta B QCV minus CPG T03, right? So yeah,
Fuel mass ratio.
what?
Here, F is noted for the ratio of that.
Correct. Yeah, so I am still not at the final answer. I am just calculating the fuel to air ratio. So once you get fuel to air ratio, then your problem is straightforward, right? What is fuel to air ratio? F is nothing but mass flow rate of fuel to mass flow rate of air. And mass flow rate of air is given to you. So mass flow rate of fuel you can calculate in terms of F times mass flow rate of air, right? All you have to do is like just multiply mass flow rate of air to whatever you get here. So once you calculate that one, I am leaving you guys for the calculation. I am not doing the numerical values what comes in intermediate steps. So you should get mass flow rate like fuel to air ratio to be equal to 0.024 something. You will get like 0.024 something. And once you know F, you can use this one and calculate mass flow rate of fuel. That has to be 2.43 because it's multiplying with 100. So that will be 2.43 kgs per second, and they are specifically asking round off to 2 decimal places. You have to round off to whatever you have to 2 decimal places. That's it. Right? Straightforward, right? This question. Right? So what I'm going to do is like I will stop here. So because I don't want to take any more numericals. Still we will be dealing these things in our classes. So I just I think like yeah. So I will stop over here. So if you guys have any queries or questions, you guys can ask definitely.
Yeah, guys. So, any doubt or any concern on this?